Hey everyone, and welcome to this explainer brought to you by Forge College. So, if you were with us for the last session on handling complex Solana transactions, you already know how to compose intricate instructions, manage compute budgets, and build out those really beautiful, optimized transaction flows. But today we're taking those skills from simply assembling transactions to actually bulletproofing them against the harsh, totally unpredictable realities of the mainnet. We are diving deep into library customization, error handling, and debugging. Let's get started.
It worked perfectly on my machine. We have literally all been there. I like to call it the happy path delusion. You know, your code works perfectly locally, you feel like a total Web3 genius, and then you deploy it and it's suddenly failing in the wild. Why does that happen? Well, it's because gremlins in the RPC nodes or thundering herds of network traffic cause unpredictable chaos. That perfectly ordered sequence of instructions you built just hits a latency spike or maybe an out-of-compute error, and it fails completely silently. But don't worry, today we're engineering a rock-solid fix for that exact chaos.
All right, here's the blueprint for today's explainer. We've got 4 parts. 1, the arsenal. 2, flavors of failure. 3, the laboratory. And 4, the blueprint.
Okay, jumping into section 1, the arsenal, let's look at our core tools.
Listen, hope is not a strategy. Instead of relying on raw connections that crash silently and just leave you guessing, we're actually going to build a custom wrapper around the Solana Web3.js library. Specifically, we'll design a function something like send with retry. Think of this wrapper as your interceptor. When you fire off a transaction, this wrapper catches any errors returned by connection.sendRawTransaction or simulate transaction, and it intelligently decides should it give up, log a warning, or try again. It's essentially putting a really smart, protective layer right between your code and the blockchain.
Now, to engineer this wrapper correctly, you have to adhere to 3 fundamental rules of solid client behavior. First up, classify your errors before remediating. A network timeout requires a totally different fix than a missing account, right? Second, instrument early. Deploy lightweight timing probes and contextual logs so that when a failure does happen, and it will, it becomes an actionable hypothesis, not some big mystery. And third, prefer small, reversible client layer fixes. Whatever you do, don't go rewriting your entire transaction logic just because of a temporary network hiccup.
And that brings us to our first major defense mechanism, which is just brilliant: exponential backoff with jitter. Let's say an RPC node is completely overwhelmed. If your script instantly retries and everyone else's script instantly retries, congratulations, you've just created a localized denial of service attack. You're accidentally attacking your own RPC node. Backoff means waiting a little longer after each failure, say 100 milliseconds, then 200, then 400. And the jitter? That adds a tiny bit of randomness to the wait time, spreading out the retry attempts to make sure we're playing nice with the network.
Moving right along to section 2, flavors of failure. Let's diagnose the error.
Check out this matrix. It perfectly categorizes our errors into distinct flavors. This proves that transient RPC timeouts and account missing simulation errors need totally different telemetry. If it's a transient timeout, you have to track the attempt number and the duration to verify your backoff logic is actually working. But if it's an account missing ordering error, timing doesn't matter at all. You need the instruction index and the missing public key. If you try to apply a timeout fix to an account missing error, you're literally just going to be retrying a fundamentally broken transaction until the end of time.
So, the huge takeaway here is that we must map these vague, raw connection failures into custom, strongly typed exceptions. Instead of your console spitting out a generic transaction failed, we wanted to throw something like this: account missing error. Notice how it carries the exact missing public key directly inside its payload. By doing this, we're giving our higher-level application logic exactly the context it needs to alert the user, suggest a fix, or even automatically reorder the instructions. It's a real game changer.
All right, section 3, the laboratory. Safe debugging. Because let's be honest, experimenting with broken transactions on mainnet is a fantastic way to lose funds and probably friends.
So we're going to run a very strict diagnostic process here. Step 1, we spin up a local solana-test-validator to keep everything totally isolated. Step 2, we inject the skeleton of our custom wrapper. Step 3, which is honestly the fun part, we intentionally break things to create reproducible cases. And finally, step 4, we fix and iterate. This loop right here, This is the absolute gold standard for Web3 debugging.
To verify our retry logic actually works, we get to play the villain for a second. We're going to artificially throttle the local validator, or literally wrap our send-raw transaction calls in a massive artificial delay. By deterministically forcing a timeout once every few calls, we can actually sit back and watch our send with retry wrapper kick in, apply its backoff with jitter, and eventually succeed. We are quite literally proving resilience through intentional sabotage.
Now, for the account missing scenario, we do something kind of similar. We purposefully create a race condition. We'll construct a transaction where instruction B depends on an account created by instruction A. But we will intentionally place instruction B first. This deterministic ordering race absolutely guarantees that the simulation will fail, which allows us to test exactly how our wrapper handles deep structural transaction errors.
And when that intentional ordering error hits, our wrapper doesn't just panic. Nope, it executes a diagnostic simulation. It actively calls connection.simulate-transaction, pulls the deep instruction-level logs from the Solana runtime, and literally staples them directly to the error object. This means when your console throws an error, you aren't stuck digging through network tabs trying to figure out what happened. All the diagnostic data you need is right there in the exception payload. It makes debugging incredibly easy.
Finally, Section 4, the blueprint. Let's document the fix.
The contrast between an amateur script and professional engineering is honestly night and day. A fragile client just gives up at the first sign of unpredictability and crashes silently. But our newly instrumented client, it embraces the unpredictability, it tags the failure with a request ID, applies our backoff strategy, and captures simulation data, completely transforming chaotic network failures into highly actionable, heavily logged hypotheses.
You are going to capture all of this vital work in a debug report. Think of this as your definitive engineering document. It shouldn't just say, hey, I fixed it. It needs to explain exactly how you reproduce the error, show the console snippets of your structured logs, provide the before and after diffs of your client wrapper, and include integration notes for the rest of your team. A report like this proves your fix is deliberate, not just some lucky accident.
So, what's next? Well, these precise artifacts, your smartly patched client, your local test suite, and your comprehensive debug report, they are exactly what you will use in the upcoming module. We'll be taking these hardened tools to plan and orchestrate reliable, real-world interaction flows in the Capstone client script. You've spent this time building the armor. Next, we actually take it to the battlefield.
And that leads us to the ultimate question for any serious Web3 developer. Will you let errors dictate your transaction's fate, or will you step up and engineer total observability? I highly encourage you to head over to forge.college to learn more about this subject, dive deeper into advanced client interaction patterns, and master all sorts of other Web3 engineering topics. This explainer was brought to you by Forge College. So are you going to stop guessing and start observing? Until next time, happy debugging!